Record. Okay, we are now recording. So we are looking at a question from chapter 4, question number 65. Sketch the three-dimensional shape of the following molecules. Okay, so the topics here that we're looking at are Lewis structures of molecules. And then we're looking at 3D shape. All right. Let's see here. Of course, I don't have my assignment in front of me. Can you remind me which ones I assigned out of this? Did I assign the whole thing?
Do you want me to read you all the questions you assigned?
Just 65. Did I assign all of question 65 or specific letters?
Oh no, you assigned the whole thing.
Okay, good. I hoped I would, because it's very important to get a lot of practice on these. You can't memorize this. I mean, you can memorize the steps on how to do these things, but practice is the most important thing. So let's see. Is there a specific structure you were struggling with, or just the general concept of this question?
The general concept. So you could just show me one, and then I could do the rest.
Okay, no problem. Let's see here. I will do. In fact, instead of exactly doing one of these, I will do. Let's see. I will choose the following. We will do, to begin with, the molecule. Let's do CHC. I don't think this is one of them. HCN is one of the ones I'll do for you. We'll start by doing that structure. And then another one, I want to do a couple for you. And I'm going to do several that aren't on that list, just purely so that you have those available to you for practice. Okay. Let's see. HCN. We'll just start there. Yeah. Let's just dive in and do HCN. So this is HCN, also known as hydrogen cyanide. It also be known as cyanic acid. There's a bunch of different names, but that's not what we're here to answer. To begin with, we want to draw this in 3D. That's the goal, right? Looking back at the question, sketch the three-dimensional shape of the following molecules. Okay, so first of all, the first thing we need to do is come up with the Lewis structure. And then the next, there's two basic steps here. Draw the Lewis structure, and then draw in 3D, assuming there is a third dimension to the structure. Now, first thing I'll ask you is, how comfortable are you with doing Lewis structures?
After doing this chapter, I feel more comfortable.
Okay. Is it primarily the second step, the 3D, that you're struggling with?
Yeah, just trying to figure that part out is really hard for me.
Okay. All right. No problem. Then instead of giving you a whole background on Lewis structures, I'll just go through kind of how to do the Lewis structure for this one. And then we will draw, well, this structure is going to, I will be honest, this structure is actually going to end up mostly 2D, but we'll get there. So to begin with, HCN, a number of ways of doing a Lewis structure, but the first thing that people often do is go, okay, how many valence electrons are there? Is one of the steps that we often do. And in HCN, how many valence electrons per hydrogen?
Oh, I'm sorry. One.
Oh, no problem. Yeah, no worries. It's all good. See, look at that. You're on top of it. How about carbon?
4.
Perfect. And finally, nitrogen.
And 5.
Nailed it. 100% without hesitation. Not surprised. 10 total valence electrons. That's perfect. Now, what's your center atom?
C.
Perfect.
Carbon.
Exactly. Completely agreed. Okay. That means, of course, you're going to draw nitrogen there and hydrogen there. Okay. How are we doing so far?
Good. Doing good.
Okay. Now, people sometimes start out by going, okay, let's then put the valence electrons around. So we've got 2, 4, 5, 6, 7, 8. And then we could do 9, 10 valence electrons like that. This is one way of doing it. So you start out by putting the valence electrons on the atom that is the most electronegative. Are you familiar with the term electronegativity?
Yes.
Okay, perfect. Perfect. Then that's why I put them on the nitrogen, because people often do that. There are a number, like I said, there are a number of approaches to this. I think you probably already can see that what you need to do is double bond and then triple bond the nitrogen to the carbon. Does that make sense?
Mm-hmm.
Perfect. Okay. So that, of course, is how you end up with the final Lewis structure that I have very, very strong confidence you would have already drawn. Had I given this to you on an exam, you would have come up with this structure.
Yes.
Boom. Perfect. Okay. Now, with that in mind, does it make sense if I say that the carbon, the central atom, is linear geometry?
Because it's in the middle?
Not just because it's in the middle, but if you look at the easiest way to have you looked at the section on geometry yet and looked at what we call VSEPR theory?
Yeah, I did read that section, and honestly, it was very confusing.
Okay, no problem. You know what? Let's dive into that then. Let's go there first. Okay.
Uh-huh.
All right. So what we're looking at then as kind of a tangential circuitous route here is we're going to look at the topic of molecular geometry and what we call valence shell electron pair repulsion. That's where the VSEPR comes from, theory. So it's valence shell electron pair repulsion theory. So let's start actually by looking at this thing, because that is a very very large number of words for a theory. So you know what valence electrons are. Perfect. So of course, just for anyone rewatching this, we'll just say that valence electrons, as a reminder, are your outermost shell electrons. They are the ones that therefore are involved in chemistry. Now, electron pairs, we know that electrons, and that's a plural, electrons are paired in orbitals. And so once you've created a molecule, generally all your electrons are going to be paired up, usually. There are always exceptions to this, but generally once you've created a molecule, your electrons are paired up and you have pairs in orbitals. So orbitals then contain pairs of those electrons. And since electrons are of the same charge, negatively charged, then what then we have to look at is, well, because they are the same charge and they are all negatively charged, then they are going to be repulsed by each other. But it's not just the individual electrons that are repulsed by each other. It's the repulsion of the orbital pairs around the atom that we're talking about here. So what that means, to jump to another slide, is very generally, you can think of the valence electrons as kind of existing in what you might almost think of as like these kind of balloon-like shapes around the rest of the atom. The valence electrons will exist in these balloon-like shapes. You can kind of picture it this way. It's not exactly accurate, but it is a good visual to think about. And so, for example, when we have that carbon atom that is triple bonded to that nitrogen and then single bonded to that hydrogen, if we're talking about that carbon atom now, then we'll make this carbon atom this guy here in the center, and we'll put like the hydrogen atom on one side and the nitrogen atom on the other. There is, of course, a second and third bond that forms there. But let's just talk about the general, but this, because the second and third bond are in the same geometry as the first bond that forms in that triple bond, we'll just think about them as being one connection to the nitrogen. Does that make sense?
Yes.
Okay. Am I moving too fast at all?
No, you're not.
Okay, cool. Please let me know if you have any questions or if there's anything that I say that is at all confusing or that you have any further desire for clarification about.
I do have one question.
Please.
So the nitrogen, it has a lone pair that's not connected to the carbon. Does that impact the shape?
It does not impact the shape because we only, when we're talking about the shape, we're usually talking about the geometry surrounding what we'd consider a central carbon, or not central carbon, sorry, a central atom. It's not just carbons, but central atoms. So
Okay.
normally when we talk geometry, you are looking at a central atom. Now let's go one step deeper and let's define a central atom. Let's actually say that for my course, because some people quibble with this, but here's how I view a central atom. A central atom is any atom that is covalently bonded to two or more other atoms. So that's the first thing. You have to have at least two atoms that are linked to a common atom for that common atom to be considered a central atom. And you can't really be in the center of something if there aren't two things on either side, right?
Okay. So like NaCl doesn't have a central atom.
So for two reasons, yes. NaCl, first and foremost, doesn't have a central atom because it is an ionic compound. And therefore, there is a different type of structural conversation you have about ionic compounds. You talk about crystalline shapes and crystalline structures, but you can't actually talk about the shape of a molecule because ionic compounds, ions in general, let's specify very exactly, ions don't form molecules. Ions form either amorphous or crystalline structures that have no defined limit to the shape. There is no, you can't just say for sodium chloride that every sodium chloride will consist of one sodium and one chloride, because we know we get big sodium chloride crystals of varying sizes. That makes sense?
Yes.
And that is the situation for anything that involves ionic bonds. So when we're talking geometry, we're looking at a central atom that involves covalent bonds. And that's why I did specify in the central atom definition is any atom that is covalently bonded to two or more other atoms, because it needs to be a covalent bond and cannot be an ionic bond. And thank you for asking your question. Do you have another question?
Oh, no, that was it.
Okay, perfect. So the geometry, we're looking at a central atom. That's the first thing. Now, molecules can have more than one central atom. Okay, but if there is more than one central atom, all that means is you talk about the geometry of each, as we're calling them, central atom independently of each other, or I should say as not even necessarily independently, but one at a time.
Okay.
You define what I'm trying to say is you define the geometry for each central atom individually. Individually, yeah. So if there are 3 central atoms, there are going to be 3 different atoms with 3 potentially different geometries, or at least each atom gets defined. It gets its geometric definition based upon analyzing it as the central atom.
Mm-hmm.
And I'll show you an example of that. Don't worry. So to begin with, before I get ahead of myself too far, valence shell electron pair repulsion theory. We're looking at a central atom, in this case, the carbon. And what you do is you treat each bond or lone pair as a electron cloud. So you look at each bond, and I'm going to use a capital B. If it's a triple bond, if it's a double bond, if it's a single bond, that gets treated as one electron cloud. And the reason for that is I like to use the analogy. A bond is like a road between 2 locations. And what I mean by that is a road can have 1 lane. It can have 2 lanes, or even 3 lanes. But it is still just that one road. Does that make sense?
Yes, it does.
Okay. So a triple bond may consist of 3 connections between the two same atoms, but it is still just one cloud of electrons bridging or linking those 2 atoms. Cool. So we look at each bond as one electron cloud, and then we also consider each lone pair, which we also call a non-bonding pair, as a electron cloud.
Okay.
So we count the number of electron clouds around a central atom. A bond, be it triple, double, or single, is one cloud, and then each lone pair itself is also one electron cloud.
Okay.
Okay. So go ahead.
Oh, I was going to say, looking back at the example that you provided, so this would have 5 electron clouds?
I'm glad you asked. So HCN, first of all, start by just counting electron clouds directly involving your central atom.
Okay. Okay, I see.
Does that make sense?
Yeah.
Okay, so therefore, go ahead.
Oh, sorry. So it wouldn't be 5 because the nitrogen lone pair is not attached to the carbon atom.
Correct. Yeah. Any of the lone pairs on the nitrogen are not directly associated with the carbon atom, and therefore that lone pair has nothing to do with the carbon atom with regard to counting electron clouds. Exactly. So therefore, how many do we have?
We have 4.
Ah, okay.
Oh, no. We have 2.
Good. Does that make sense?
Yeah, because the triple bonds were confusing me, but there's still just 1.
Exactly.
Okay.
Yeah, exactly. That's why I took the time to try to spend a few minutes saying that a triple bond is still just one electron cloud. Hence, this slide, look at each bond, be it a triple bond, double bond, or single bond, as one electron cloud. It is one road between two atoms. It has 3 lanes, but it's still just one road.
Got it.
Exactly. Yeah, perfect. Now, what electron pair repulsion theory says, so valence shell electron pair repulsion theory says is the electron clouds, the valence, more accurately, the valence electron clouds around an atom will repulse each other and space themselves accordingly as equidistant as possible around that central atom.
Okay. So it doesn't matter if, like in this example, one of them is a single bond and the other one's triple, they're going to be the same distance.
It doesn't, well, so what I mean is when you have that carbon, we're not talking about the distance between the carbon and nitrogen and the distance between the hydrogen and carbon. That's a different topic. What we are talking about is this electron cloud, these electron clouds, and how they decide to geometrically arrange themselves in relation to one another around that central atom. So when it comes to just their geometric arrangement, kind of the angle, if you will, you should get a basically linear. So the geometry here is going to end up being what we call linear, because we've just got 2 clouds, and so the most equal angle between the clouds is 180 degrees, spaced out in this case 2 dimensions around that carbon atom, and that gives you this kind of linear on opposite sides of the carbon atom.
Okay, that makes sense.
Okay, good. Now let's look at a few more complicated examples. Because I think
Actually,
that one. Yeah.
actually, sorry, not to cut you off,
No,
but I do have to go so that I can make it to class on time.
not a problem. Not a problem. You got it.
Okay. Thank you.
You bet. Okay. With the current person having left the chat with me and the recording still going, let's actually continue to talk about this topic. So rather than diving into a long theoretical lecture, let's use examples as a way to establish a further explanation of valence shell electron repulsion theory and molecular geometry. So if we take something that now has, so we started with a central atom that had just two other atoms attached to it. Now let's go with something that will have three atoms attached to it. So in this case, a very good example of this, due to its very nature of being an exception to the octet rule, is the behavior of boron. Now, boron, let's start by doing the Lewis structure. Yeah, that's the best place to go. So, Lewis structure for boron trihydride. Now, first and foremost, number of valence electrons. If we look at that, number of valence electrons, boron from your periodic table has 3 valence electrons, and there's 1 boron. And then we add to that the 1 electron from hydrogen, and there are 3 hydrogens, giving us, of course, therefore, 6 valence electrons. You figure out in general which one is your central atom by typically placing the thing that could be less electronegative in the center. However, the rule doesn't work with hydrogen at all, because hydrogen can only ever form 1 bond. So hydrogen can never be a central atom. Therefore, we have to put boron in the center. Let's start then, after that, by attaching each hydrogen to a boron. And we have done that in this case here. Now, we've used up our 6 valence electrons. You can see each line represents a pair of electrons. And therefore, since we have used up our 6 valence electrons, this is the Lewis structure of boron trihydride. There is no octet for boron. Boron is an exception to the octet rule. We've already said that hydrogen is an exception to the octet rule. So that is where we are. This is the final valence, final Lewis structure. Now, if you have listened to any of the lectures that I posted that talk about formal charge is a great way to test the stability of your Lewis structure and the validity of your Lewis structure. And without diving into the details of that terribly, I'll just remind you that the way to calculate formal charge per atom is to take the number of valence electrons an atom starts with, and then you subtract from that number of things surrounding the atom. Okay, so it's number of valence electrons. Let's rewrite that actually. Let's rewrite that. So number of valence electrons the atom starts with. Usually we would utilize our periodic table to determine that, minus number of things surrounding the atom once it's in the Lewis structure. So hydrogen here, the formal charge is, it starts with 1 minus, it's got one line drawn to it, so it's 0. This formal charge on this hydrogen is, it starts with 1 valence electron, as the periodic table tells you, as we counted for our valence electron calculation, minus 1 line drawn to it. And finally, this hydrogen here, formal charge is 1 minus 1, giving us 0 and 0. And let's not ignore or forget about the boron. The formal charge of the boron is 3 valence electrons that it starts with, being in the third group of the main blocks of the periodic table, minus 3 things surrounding it, giving us a formal charge of 0 for that boron as our central atom. So you can see that this actually is a very stable structure. There is no formal charge. Okay. Now, we know that this is the Lewis structure, the boron trihydride. Let's therefore take this opportunity then to look at the geometry of this thing. Now, remember that valence shell electron pair repulsion theory says that each bond, be it a single, double, or triple bond, is 1 electron cloud. So that molecule that we just drew has, here's the structure again. Let us say, therefore, looking at this thing, what is the number of electron clouds around boron? You look at it, you go 1, 2, 3. The answer to that question, therefore, is 3 clouds. Next, those clouds space themselves equally around the central atom. What does that look like? Well, boron, therefore, goes in the center, and we end up with 360 degrees divided by 3. 3 things spaced evenly around an atom will still be perfectly fine in 2 dimensions. There we are. So 360 divided by 3 gives you what value? Take a moment if you need it. The answer to that question, of course, is 120 degrees. And therefore, since it's 120 degrees, you end up with essentially thirds broken up. These are all 120 degrees, like so. Now, there is a name for this geometry. The geometry here is called trigonal to start with, because it is 3 parts. And because they are all in the same plane, because it's a flat surface lying in a plane, this is called trigonal planar. So the geometry of this shape is trigonal planar. Now, what would be the next option of what we would like to do here? That is the first shape we've come up with. What's next? Well, let's look at another structure. The next structure we would start with would be something probably with potentially 4 bonds to it. So the easiest thing to do is to look at a carbon atom with 4 atoms attached to it. For the ease of comfort here, let's simply do good old methane or carbon tetrahydride. So that's carbon with 4 bonds. as we have a student arrive here with some questions, I'm going to wrap this structure up very quickly as I can and then answer those questions. So to begin with, the structure that we are looking at is carbon tetrahydride, and that would be carbon with 4 hydrogens attached to it. So very quickly, number of valence electrons, carbon is 4 plus, and of course there's one of those, and then you get 1 from each hydrogen, multiply that by a 4, gives you 8. So we know that carbon is the central atom, hydrogen, 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 hydrogen. You can see we used all 8 valence electrons. You can go through and look at the formal charge on each atom. We'll just look at one hydrogen since they're all identical. It's 1 minus 1 gives you 0. Formal charge on the carbon now. Remember, it starts with 4 valence electrons that the carbon would have started with, minus 4 things surrounding it, giving you 0. So in this case, the formal charge on all atoms is 0. Therefore, this is the most stable structure. And this is therefore the structure of carbon tetrahydride. Now, let's jump to the geometry. Now, once you add a 4th atom into the mix, you can't space these out just in 2 dimensions. You have to actually go to a 3rd dimension. So this is going to be the first shape that we have that is 3-dimensional. And that essentially looks like carbon in the center. We draw in 3 dimensions, something that I will go over hopefully in another lecture or is covered on the website. You put 2 atoms in the plane of the page, hydrogen and hydrogen, and then you draw a 3rd one emerging from the page by using a wedge that is growing larger away from the carbon atom. There's the hydrogen. And then you do a dashed or dotted line kind of receding away from the carbon, almost disappearing into the page. And that is our 4th atom. And that is in general what this would look like. The name for this geometry, the name is tetrahedral. So we're going to finish that structure in this fashion. As you can see, that is where we are. We'll come back to this topic either in a different lecture that you watch with one of my talented colleagues around the world, or I will cover this in another lecture as well. Okay, pausing now to interact with another student. So recording started again. We're looking at chapter 4, question 53, expanding the following condensed structures into the correct structural formula. So in general, what you're doing with this is you're really just taking this and turning it into a Lewis structure. You're basically translating this into a Lewis structure. And these condensed structures actually contain most of the information you need anyway, if you understand how they work. And that, of course, is the big if, of course. In general, so with condensed structures, typically, we can say that you place, I think they say this in the book, but then again, it's been a couple of hours since I've read it, so I've already probably forgotten. You place the hydrogen atoms in front of any atoms they are bonded to. If more than one hydrogen atom is attached, you show the plurality. Are you guys comfortable with me saying the word plurality? Because I literally have coworkers who would have called me out and said that's too big of a word to use in my presence. So I just want to make sure that you guys are okay with that, which I suspect you will be because that coworker of mine, anyway, is a fool. To show the plurality of attached H atoms, So atoms attached, you show the plurality of attached H atoms with a subscript. Then basically consider anything in parentheses as a whole thing attached to the atom directly left of those parentheses, hence this guy on A, that CH3 2 means that there's two of those attached. So that this means that there are two of those CH3s attached to the carbon before it. And literally what you're doing is you're looking at what we call what you're trying to do is look for the kind of primary chain. And then 2, consider the things attached. Not condensed. Consider attached stuff. So the way to explain that essentially is to say, if you're looking at those questions, then the central chain, for example, on A is carbon, 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 oxygen, carbon. That's the central chain. And then these hydrogens are attached to that carbon. These hydrogens are attached to that carbon. This oxygen is bridged between those two carbons. And then you've got this hydrogen attached to the last carbon along with two CH3 things attached to that carbon as well. Okay. So again, I will do this for most of the things that people ask about homework problems. I'm not going to do the homework problems. And the only reason I'm not going to do them is because I want to leave them for you guys to actually do as practice. It's not about giving you the answers, because honestly, you can find the answers online. You can find the answers in the back of the book typically. And yes, if you really want the answers, fine, I'll give them to you. Sure. But it does you less benefit for me to give you the answers than for me to show you examples that look like them. So with that in mind, let's actually just create one real quickly for that. Let's go CH3, N, CH3, 2, for example. Okay. So what this structure means is we've got a CH3. Actually, there's what I should do. Let's make that structure a little bit more interesting, because otherwise that would actually be a bad thing to write that way. Let's do CH2, O, CH2, CH3, and say that we have 2 of those. Now I've really got myself into a corner, because now I've created this really large thing that there are 2 of, but that's okay. I'm good at structures, at least I hope. So the really, really central atom here is, in essence, the nitrogen, because you've got one CH3 thing that is attached to this nitrogen, followed by 2 of these things in the parentheses that are also attached to that nitrogen. Does that make sense? Okay. So I start out by drawing a nitrogen for myself. Then I'm going to put 1 carbon, a hydrogen, a hydrogen, and a hydrogen, like that. That's the CH3. So this thing here is this thing here, like so. And then I need to draw 2 of those things in the parentheses. So we'll go carbon. I'm just going to first do the chain. Carbon, oxygen, carbon, and then finally 1 more carbon, like so. Okay. And then coming off that, there's another chain that looks like that. Carbon, oxygen, carbon, carbon. That's how I'm going to start. So I can show you guys There's two chains that look identical. And that's why you've got the subscript outside these parentheses. There's two of those. Okay. Now, the next thing is attached to this carbon. There are two hydrogens because this carbon right here is this carbon right here. Okay. And the same thing goes for this. These are identical. So this is a hydrogen and a hydrogen, a hydrogen and a hydrogen, like that. Now, jump to the next atom is the oxygen. Now, the oxygen has two things attached to it. What I'm showing you guys here is, in essence, actually a really rapid drawing of a Lewis structure. And this comes from lots of practice and just lots of experience and knowing what these things should look like. Now, an oxygen with two bonds to it still needs an octet. Okay. Remember, we always go back to the octet rule. So because there's an octet, there's got to be two lone pairs on that oxygen. If there's two bonds, there needs to be two lone pairs as well to give it an octet. Each bond contains two electrons. That means I've got 4 electrons on that oxygen as well. The only other way to get an octet is to put two non-bonding pairs on. Okay. Now, so that's that oxygen there. This oxygen here will also need two non-bonding pairs. That's that oxygen right here. We're talking about this guy. That's the oxygen right there. Finally, we come down and look at, we've got carbon, carbon. So that's that carbon and that carbon. We've got this carbon here. Let's do first the first carbon. That's got two hydrogens attached to it. That's that carbon. And finally, our very little carbon on the end with the 3 hydrogens. 1, 2, 3. 1, 2, 3. So that is how you take a condensed structure or condensed structure and draw the expanded structure from it. All you're applying is the patterns and the rhythms and the essence and the general principles of Lewis structures. And when it comes to a condensed structure, they are typically used for larger things. The whole idea of using a condensed structure is to literally condense it down and make it faster to write. And you do that for big things. You don't have to do that for simple molecules because they are so simple that they don't need to be condensed. But large things, as you can see, this thing is pretty big compared to the Lewis structures that you've probably been seeing in most of your homework. Therefore, the expansion in this way is also generally going to be for molecules that follow a lot of the same patterns of what you expect, especially for this class. For an introductory course, we're not going to throw something incredibly huge at you. I'm not going to ask you guys to draw one of the molecules involved in DNA. Okay. I'm not even going to ask you to draw the structure of caffeine. I'm not even asking you to draw the structure of benzene. No, because benzene is not an easy one to do. I'll show you why. Benzene, it's a beautiful structure, by the way. Benzene is really awesome. It is a very elegant structure. It is C6H6. Now, there are actually 2 very different compounds that exist for C6H6. The one that most people would draw, if you didn't know exactly what benzene was, would be carbon, 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 1, 2, 3, 4, 5, 6. And then you'd put a hydrogen and a hydrogen, and you'd put a hydrogen on each carbon, like so. And then you go, okay, how do we complete this with an octet? Well, this carbon here, let's just go ahead and put a triple bond to it, because that's now 1, 2, 3, 4. And that means this carbon here has now got 1, 2, 3, 4. So they both have an octet. Perfect. Let's come next to this carbon here and do a triple bond. That gives you now 1, 2, that doesn't work. Do you see why? You see 1, 2, 3, 4, 5, which means we'd have put 10 electrons there. That doesn't work. I have to actually remove that. Now here you have 1, 2, 3, 4. Okay. We come to this guy here. We'll put a double bond again. And does that actually work? Let's see. Exactly. Good. Yeah. So that needs to be double bond, single bond, double bond, single bond, double bond. What am I missing? 1, 2, 3, 4, 5, 6. There is something missing here. This is actually very embarrassing. C6H6, blah, 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 blah. Oh, I know. So that's 4 there. Yeah, this you can't actually draw this structure as it is. You guys see the problem with that? I can do a octet here, an octet on this one, an octet on that one, and an octet on this one. But how do you get an octet on this carbon? I've got C and I've got 1, 2, 3, 1, 2, 3. Anyone? It's on both sides, exactly. That's a major problem, right? So what you end up doing, there is a way to do this, and my brain, because I'm doing this too fast, is completely, of course, melting down on me. So going, what the heck? Why did you ever go into studying chemistry? Right? Okay, so to begin with, chemistry is awesome. So if you were to do a triple bond like that, you can't actually put a hydrogen there. That becomes a problem. But what you can do is put a hydrogen there. And then let's say we did 2 triple bonds like this. You can actually then remove this hydrogen. So see how we have 4 and 4, and you can actually just put this hydrogen here. That is a structure that works. Okay, that makes sense so far, guys? Okay. There are other structures. Even as I do this, my brain starts to see how I can manipulate this into other things. But this is one option for that structure, for C6H6. Okay, this works for the octet row. Every single carbon has an octet right now without having too many atoms. Okay. There is another structure. It's a ring structure. 6 carbons in a ring. And this is the one that I was wanting to get to. This thing is the structure of benzene, because this thing at the top is not benzene. That has a different name. But it is a name in organic chemistry, so we're not going to bother mentioning that. Benzene is actually technically an organic chemistry name as well. Okay, so this is the basic ring structure that exists. And then you can either double bond it in this way, or for simplicity now, I'm just going to draw a hexagon. Carbon, 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 carbon. You know that there are hydrogens attached to each one of these. You can also double bond here, double bond there, and double bond there. And you can see that it's either a double bond here, here, and here, or the opposite sides, flipped around. Okay, what you're literally doing is moving the double bond here, moving this double bond there, and then moving this double bond there to get this structure. Or you move it back, move it there, and move it there. Okay, you guys follow what I'm saying so far? I know I'm moving really fast, and I'm showing you guys something actually somewhat advanced, especially with this class. Okay, that being said, because you have these two things that exist, and these structures are equal to each other, but they are distinct structures from each other, neither one of these is the actual structure. When you have two structures that are an option that are equally stable, and the electrons can move this easily, what happens, even more fun, is you get to this topic called resonance. Now, this is not a topic that is even something you have to worry about for this class, but I wanted to show this to you because it's really cool. Okay, this is some when you get into the more advanced chemistry is when it really starts to get fun. You really start to talk about stuff that has some crazy implications in your life. So resonance means neither individual equal, we could call them flip-flopping structure, is the real structure. They are just like snapshots of the structure that could exist, or that does exist. The real structure is a hybrid of both. And what that means is, imagine that hexagon of carbons. So we're just going to show just the hexagon now. There's no double bond there. You actually have double bond nature spread out across all 6 carbons. And those electrons actually are shared amongst all 6 carbons. They all have double bond nature, making this structure super stable, far more stable than you'd expect it to be. The calculations on benzene that you do without considering it being benzene, without considering the electrons being shared, do not work, because it doesn't account for this resonance hybrid structure. This resonance hybrid structure is something out of the ordinary. Even more cool, when you get what we call delocalized electrons, so the electrons are delocalized across all 6 atoms. When you get delocalized electrons like that, that is how you start to get color. It is with delocalized electron clouds that pigments exist. Without delocalized electrons, in general, you would not have pigmentation. You would not have color, because there wouldn't be enough of an electron cloud for photons to hit and actually reflect and produce observable light in the way that we are used to seeing. Even more, there's so many crazy things about this. Another crazy thing about this, the electrons actually move in a circular motion in that flat surface of the carbons. They move in a circular motion. That circular motion of electrons generates a magnetic field around this benzene ring, because anytime you have electrons moving, that's the movement of an electrical field. And when you have the movement of an electrical field, it generates a perpendicular magnetic field. Okay. So none of this stuff is going to show up on the exam. That's why I'm going to stop here. But what I'm trying to do is show you that this stuff gets really cool. Okay. It gets really cool and really interesting. Now, we're going to stop there. I'm going to stop answering questions. I'm going to stop recording, and we will call it a night for recordings.